Hi, this is John, and I built a transformer, and I will run through the code that I have written. So first of all, we are importing NumPy, Matplotlib, and Cbonds. NumPy we are using it for numerical operations. Matplotlib it is used for visualizing attention weights and positional encoding, and Cbond we are just using it for visualization purpose. So over here, I've written class multi-head attention. So it is used for implementing multi-head attention, and it allows the model to focus on different parts of the input sequence using multi-attention heads. So this class implements the multi-head attention mechanism. So as I told you earlier, that each head operates on a smaller decay dimension, and this class it enables the model to capture different relationships in a sequence, by using different multiple attention mechanisms written in parallel. So over here, we are initializing the multi-head attention module. So the D model, we are initializing it. It is the total embedding dimension. Num heads is the number of attention heads, and dk is equal to D model divided by num heads. That is, each head operates on a smaller dk dimension. And over here, we are initializing the weight matrices WQ, WK, and WB. So these are all learnable matrices to transform input embeddings into queries, keys, and values. And WO, it is the final projection matrix to recombine the heads. Then we are splitting the inputs into multiple heads. So we are reshaping the X from batch size, sequent length, and D model into batch size, num head, sequent length, and DK. And we are D underscore K, and we are transposing it as well. Over here, you can see transposing 0 to 1, 3. So it swaps the dimensions so that each head gets a separate slice. So over here in this function, we're splitting the last dimension for multiple attention heads. So now we are computing the scaled dot product attention. So over here, we compute the attention scores. So over here, you can see the attention scores is equal to mm, um, okay, sorry. Over here, you can see the scores that we are computing. So np.matmul. So we are scaling it by square root of dk, and we're using the transpose what we used earlier, and we are calculating the similarity scores. And then we are applying large negative value for mask tokens, and then for stability purpose, we are doing that. Then we are computing the weighted sum of values, and then we are computing the weighted sum of values. So over here we are using a mask, right? So this mask is being used to prevent attending to padding tokens, and the softmax is used to normalize score, and this outputs weighted sum of v. So that is what we are defining here. Now we are defining the forward pass of the multi-head attention. So we are applying the transformation. We are applying transformations to get Q, K, and V, and then we split them up into multiple heads. So over here, you can see we are concatenating attention heads and applying final linear transformation. And then we are computing the attention and we are computing the attention and we are merging the head back. So it's a basic process of concatenation. So over here, we have written the position-wise feed forward, that is the position-wise feed forward network. That is, we're implementing the position-wise feed forward network used in each transformer layer. So we are initializing the feed forward network, and we are making first dense layer, second dense layer, and we're adding the bias for first layer, and we're adding the bias for second layer as well. So we are applying two dense layers. So we are applying two dense layers, and you can also see the first transformation, the second transformation, and we're putting a ReLU activation function in between. And then we are expanding the representation to GFF representation. We are making So we are expanding the representation to DFF before projecting it back to D model. So over here, so we are putting the DFF D model. So we are expanding the representation. So over here, we have put up the layer normalization part. So this process, so we are using a small value to prevent any divisions by zero, and we are using a scale parameter, and we are applying this layer normalization so that the learning could be stabilized. So we are calculating the mean variance, and we are doing the centers and scale input, and we also have to make sure that we prevent internal covariate shift. So we have to make sure that we don't do that. Then we initialize the transformer encoder layer. So in this layer, we are putting up the self-attention network. That is, this is applying the self-attention followed by the feed-forward network. So over here, you can see the attention network is being defined, and then And then you can also see that we are using layer normalization to stabilize the training part. So then we come to this part of positional encoding. So transformers, since they don't have any recurrence or convolution like RNNs or CNNs, so we need positional encoding to introduce order information to the sequence. So this is the implementation of the positional encoding. So over here, we see position is equal to np dot a range 0, comma, max sequence length. So we have written it over here. So this creates the frequency terms for different dimensions. So these two lines of code will create frequency term for different dimensions. And we have defined sine and cos over here as well. We need alternate values to create periodic patterns. So in the sinusoidal way, if we have to generate, that is why we are putting up both sine and cos. And then over here, we are adding positional encoding to our input encoding. So we are taking the input encoding X and we are adding the position encoding as well to it. Over here, then the full transformer model, it consists of multiple encoder layers. So you can see the encoder layers over here, and then the positional encoding part, we are adding it to the embeddings, and then we get a output layer, a final output layer after passing through. So then we are initializing the transformers over here, and we are using a placeholder for embeddings as well over here. After position encoding, we are using this placeholder for embeddings. So then we do the forward pass through transformer. So over here, we see that the input is X, which is the input tensor of shape, and mask is optional, and it returns the transformed output or the list of attention weights from each layer. So over here, we are applying the embedding. In practice, it would convert input token to vectors, and we are adding a positional encoding as well. So we are looping through encoder layers in this part of code, and we are storing the attention. Over here, you can see that we are storing the attention weights for visualization. So then we are writing the helper functions. So we are writing the softmax function. We all know that softmax functions are activation functions. So we are using it to compute for each set of scores in X. So it is used basically for normalization. Then we write the ReLU activation function. So ReLU, we know it is the rectified linear unit. So we are writing the ReLU function as well. So it returns the maximum of 0, comma X. Then we write the dropout function. So it randomly drops some elements so that we could eliminate overfitting completely from the picture. So then we are writing the visualization analysis function. So over here, in order to visualize attention weights for a specific layer and head. So this part of code, we get the attention weights per specified layer and head. We get the first batch, and it displays attention weights using a heat map. And then it shows how the model focuses on different parts of the input. And that is why with this heat map, we can achieve it. So so over here, we are printing the statistics for each layer's output. So we run this part of code, we could generate all the statistics part, and then we come to the analyzing attention patterns. So we are analyzing the attention patterns across layers and heads. So it calculates the statistics about self-attention. So this piece of code, it calculates the statistics about self-attention. And we also see that we are measuring self-focus and entropy as well. So that is why I see we are calculating entropy and we are calculating the self-attention score as well. So then we are analyzing the positional encoding. So positional encoding, we are printing out the encoding analysis as well. So over here, we are calculating the mean, standard deviation, and we are printing them out. Just a second, yeah. So we are calculating standard mean deviation. We are analyzing the frequency patterns. So we are analyzing the frequency patterns of positional encodings over here. So then we write so in order to run the transformer model, we write the main function. So we create a transformer default parameters, and we create a sample input, and we store the immediate layer outputs and on a random input, and we do the forward pass. We print the statistics and we visualize the attention. We analyze the attention patterns, position encodings, layer statistics. We are plotting the position encoding patterns, attention weight distribution, attention statistics for each check. So this is how the code I have written in first. So I'll run the code now. So as I run the code, so you can see over here, the input shape is 210,512. The output shape 210,512. Number of attention layer 6, the number of attention heads per layer 8. So over here, you can see this is our heat map for layer 0 and for layer 0. And this heat map, it represents the attention weights between query and key positions. And each row corresponds to a query token, and each column represents the attention assigned to a key token. Most values we can see hover around 0.10. It indicates that even attention spread, but sometimes dark and lighter areas suggest certain tokens receive higher or lower attention. So, which in turn this helps us interpret which parts of the input the transformer model is more focused on. So, with the help of heat map, we could achieve it. So, I'm closing the heat map, and over here, you could see over here, you could see the line plot. This is for the position encoding analysis. So we see that the position encoding follows a sinusoidal pattern, sine and cos. It follows a sinusoidal pattern, which ensures that each token position has a unique encoding and different dimensions, 0 to 9, different dimensions from a range of 0 to 9. Over here, I think you can see, I think the colors we have been denoted in such a way. It showed the periodic variations, helping the transfer model capture long range dependencies. And these encodings help differentiate positions in the input sequence even without recurrence. So as I close this, so this one, it is the histogram plot of the attention distribution across layers. So over here, we see that this plot shows the distribution of attention layers for each transformer encoder layer, and the distribution remains uniformly spread, relatively uniform across layers, suggesting that attention is evenly spread across different tokens. And we see that minor variations. Over here, we could see some minor variations. It indicates the later layers might refine attention by focusing more on specific key tokens. So over here, we could see all the statistics that we all printed out for every head, for every attention, self-attention score. So we could see for everything, the statistics, layer 5, for every individual layer, we have printed out the maximum attention, mean attention, and the attention sparsity. So we have built the statistics, sorry, we have built a transformer. We have put up the every part of it, forward pass, position encoding, the encoder decoder structure. And it has been a very good experience for me building a transformer from scratch. And I want to thank Professor John for this great and wonderful opportunity.